No, no. Everything comes from here.
Oh,
so
okay,
we're just going to move a little bit this.
Okay. All right.
I hope it works. Okay, so now we have info as a source of substructure in protoplanetary disks by Calcino. So I have 15 minutes. I will let you know 3 minutes before.
Cool, thank you. Yeah, so I've been working on infall on evolved class 2 protoplanetary disks, and I'm going to show you some of the results of some interesting simulations I've run. Just to start off with observational motivation, we all know that protoplanetary disks have loads of substructures in them. We have like really rich, abundant spiral structures like we see in AB Aurigay, to like kind of more ordered M=2 kind of spiral structure seen in MWC 758. And then if we go to millimeter dust grains, we can see kind of like intricate ring-like structures, and also large central depleted cavities. So there's a few ways that people have hypothesized that you can make these substructures. So planets is obviously the one that people like to talk about the most, but potentially also ice lines or gravitational instability is also known to produce lots of spirals in the disk. But in most cases, we have we observe substructures, but in most cases, there's no direct link to any physical phenomena, and it's still mostly just a hypothesis. But there's one thing that we must not forget, and that is that most protoplanetary disks are not actually in isolation. And so this is a figure from Antonio Graffi's 2024 paper showing the torus molecular cloud. And this kind of like red emission here is 100 micron thermal emission, and it's just showing locations of lots of different disks. So there's AB Aurigay up here, MWC 758 over there. And these insets are sphere observations. I mean, it's not the sample is not totally complete in torus, but there's a lot of disks that have been imaged in torus. And the kind of interesting takeaway from this is 30% of the disks that have been observed with sphere in torus show some kind of diffuse emission that's not clearly associated with the disk. And so you can see kind of like SU-AUR up here is a pretty amazing example. So given that the free fall timescale for this material should be on the order of like 10 to the 4 years, and the disk lifetime is say 10 to the 6 years, the fact that we see 30% of disks have this kind of diffuse emission around them is kind of surprising, I think. So motivated by that, I took it upon myself to do some simulations with infall. So the main objective of this project is to study the effects of a streamer like infall. So basically, I'll talk about the setup a little bit later, but we want to understand how what this infalling material can do to an initially unperturbed disk. Can we generate spiral arms? Can we generate disks, gaps and rings and dust? And how long do these signatures last for? So this is just a crude diagram of what the setup is like. We start with some kind of like elliptical streamer, elongated streamer-like object that's initialized at some particular radius, and it has a major and minor axis. And we set a mass for this ellipse, and the particles in the ellipse are initialized on a free fall orbit, and with some like inner radial distance that the parabola will reach from the central star. So for most of what I'm going to show you here, the infall mass is only 10% of the disk mass, and the closest approach of the streamer material is 100 AU. And a kind of over the timescale of the infall m dot is only about 10 to the minus 7 m sun. So it's actually not that large, despite being 10% of the mass of the star, and assuming like a 1050 Jupiter mass protoplanetary disk. So this is showing the time evolution of the simulation from when the streamer initially interacts with the disk. You can see that it excites some spiral arm structures, and it produces spiral arm structures the entire duration that the infall is interacting with the disk, which lasts about 10 to the 4 years in this simulation. And by the end of the simulation, the simulation I've run for much longer than this, but the spiral structure, it's not very clear on this screen here, but the spiral structure actually persists for quite a long time after the infalling material has completed its interaction with the disk. So a couple of just interesting things I noticed about the spiral arms. One thing is that the pitch angle of the spiral arms is kind of peculiar. So the infalling material hits the outer disk here, and this plot here, it's tracing, I basically use like a spiral fitting algorithm to like trace the spiral arm in the surface density of the simulation. And this is the coordinates of that trace here in the black line. So large R up here is an outer radial region here, and as phi of 0 is, I just define the tip of the spiral as phi of 0. So this is just tracing the spiral in R phi. This beta parameter here is the pitch angle of the spiral arm. So a large pitch angle, this is the definition, it's dr over r d phi. So a large pitch angle would mean dr is greater. So the spiral is more radial. It's pointing more towards the center of the disk. But a low beta would mean that the spiral is more tightly wound up. So it's more circular. So you can see that from the region where the spiral is excited, the pitch angle is quite large. And then as it propagates towards the inner region of the disk, it becomes more tightly wound up. Now that's quite similar to what a massive planet will also do in a protoplanetary disk. So this is just a figure from Dong et al. 2015, where he put a multi-Jupiter mass planet in the outer regions of the disk to show that you can generate multiple spiral arms. And this is a figure from Bay et al. 2019 showing that the pitch angle of the spiral arm increases as you move towards the location of the planet. And so potentially in some cases, maybe you could confuse the morphology of spiral arms induced by infall when they're full of spiral arms produced by planets, since they look qualitatively quite similar. But there is a way to distinguish between them. So planets, obviously, they orbit in the disk and they move around at the local Keplerian rate. However, with infall, the infall is always hitting the same part of the disk, and so it's exciting spiral arms at the same region in the disk. And so what that leads to is that some of the spiral arms actually don't move as a function of time. So this is a space-time diagram here. So azimuthal coordinate on the y-axis for three different azimuthal slices in the disk. So just kind of illustrating here on this little subfigure. And I'm just plotting what the density is along this like narrow annulus as a function of time. So anything that's moving with the local Keplerian rate should have an angle on this plot of about this. But you can see that some of the spiral-like structure actually doesn't move with time. And so that was a way that we can distinguish infall-induced spiral structure from other mechanisms such as gravitational instability and from planets. So not all of the spiral structure is stationary, but it's just the main spiral arm that the infall itself is generating. There is other spiral structure that moves around with the kind of more Keplerian-like angular velocity. So this is a few more space-time diagrams showing the azimuthally averaged surface density as a function of radius and time, and the eccentricity and argument of periapsis. So this density here is azimuthally averaged as a function of r, but for eccentricity and argument of periapsis, it's done as a function of semi-major axis. So you do this because if you azimuthally average as a function of r for eccentricity, you're going to get a spurious eccentricity due to the gas pressure support. So you can see here at the start of the simulation, the eccentricity in the disk is 0 everywhere, showing that it's not, basically showing that the way that I'm measuring these eccentricities is kind of correct. And the infall hits the outer disk region and then propagates towards the inner region. And for 10 to the 5 years after the infall has completed, an eccentricity of about 0.1 persists in the disk. I won't really go too much in the argument of periapsis. So another interesting thing is that not all of the infall material becomes immediately bound to the disk when it interacts with the disk. So this is a figure showing what the environment around the disk is like after the infall has kind of made its initial passage past the disk. So some of the material hits the disk, but is still on some materials unbound, but some materials still bound, but on a high on a very high orbit. So it basically recalls around and reaccretes back onto the disk. But you get these kind of weird pitch angle changes in spiral-like structure in the outer regions around the disk. I think this is basically because some material, infall material, hits the disk, exchanges angular momentum with the disk, but then quite close adjacent to that material, some other infall material might not really strongly interact with the disk, and so it has a different angular momentum. And the boundary between this interface, you get a sharp change in the pitch angle. And interestingly, we kind of do see these features, these kind of peculiar pitch angle changes in around some disks that are candidates for currently having infall. So for the last part of my talk, I want to talk about this system, AB Aurigae. It has a crazy amount of spiral structure, a central cavity, also full of spiral arms. And recently, a paper led by Jess Speedy showed that, so they got some really beautiful ALMA data on this source. And she did a really fantastic analysis looking at the residuals from the moment one, showing that you get this kind of spiral-like structure in the velocity residuals and also in the moment zero. So we see spiral arms in the moment zero and in the scattered light, which can be correlated with each other. And she showed that if you also look at the location of some spiral arms, such as this spiral S5 down here, and you look at the location in the velocity residuals, the velocities are, so along this axis here, you're dominated by radial velocities because sine theta. So like it's major, this is the minor axis, and sine theta here equals 1. And that's a term multiplied by VR. So the VR, line of sight VR, is the strongest along this axis here. And they find that there's an excess, well, a converging pattern in the velocity residuals. So their interpretation of this is that, okay, thank you. Their interpretation of this is that this disk is gravitationally unstable, and in a gravitationally unstable disk with spiral arms, the spiral arms have more mass, and so the potential is deeper, and so the material surrounding the spiral arms wants to fall into that potential rate, and it does so mostly in a radial fashion. And so if you look at it in the lab frame, you have a spiral, everything around the spiral wants to move radially in towards it. But if you project that onto the sky, you have a line where VR is moving tangential to the line of sight, so you don't see it. But along the minor axis, you get the max kind of projection. And so this is what they were saying, that what they were seeing in AB Aurigae. But we know that AB Aurigae has infall, and even with just relatively small backyard telescope, you can even see a reflection nebula around AB Aurigae. And with the same ALMA data, Jess was able to find that there's stream of material that's falling kind of with the infall, with a free fall velocity interacting with the disk. And at the region where it interacts with the disk, there's a bright spot in SO kind of, which is used as a shock tracer. I'm going to skip this slide and just show that. If I run a simulation with infall, and I use two streamers kind of hitting a region of the disk in a similar location to where this SO spike is observed, we can also reproduce the spiral structure seen in scattered light. We can reproduce the kinematic signatures from the deviations in moment one with the radially converging velocities. And we get a bunch of spiral humps that are also seen in moment zero. So where to from here? Well, there's a lot of other disks that are well studied and potential sites of planet formation that also appear to be interacting with their environment. And so I think we need a little bit more of a systematic understanding of how infall can produce substructures in protoplanetary disks, and whether or not potentially in other systems that have infall where we see substructures in millimeter dust, whether these could also be produced somehow by infall. And I'll just finish up by saying that in AB Aurigae, there is infall. There may also be gravitational instability. There's not really any way to rule it out, but I would argue that because there is infall and infall can make the same signatures, it's going to be kind of hard to try and constrain any properties of the disk mass when infall makes the exact same signatures as gravitational instability. And that's all.
Planning, time for questions.
Is the streamer coplanar with the disk or comes at an angle?
So the two streamers have different angles and they're both out of the plane of the disk. So one's about 30 degrees above the disk and the other's about 50. And yeah, so that kind of leads to interesting things when it collides with the disk. You get like vertical velocity oscillations in the disk as well. Yeah, in my simulations. Yep.
So is the TUQ always higher demand locally when the streamer hits the disk? Is it locally gravitationally stable?
I didn't really look at this because I never included self-gravity in this simulation, but the disk mass kind of by my assumptions is not high enough to be
The disk in general, because of that locally, it could be interesting that
yeah, I think I like your idea. I'd be a little bit concerned about how we'd have to treat the thermodynamics though. But at this, because you know, at the site where the infall hits the disk, you do get very large densities, which probably could be gravitationally unstable, but it would need a careful treatment of the thermodynamics to study that, I think.
Claudia?
Can you try to evaluate the local change of mass that you have in the region in which you have the infall?
We need to repeat the question. Can you evaluate the local change of mass when the streamer hits the disk?
How do you I haven't thought about.
You can control where the streamer impact the disk.
Yeah.
Because as Sam was saying, even if you don't want to simulate it, you can try to check if the infall, so the change of mass locally, is giving you a high variation enough to then, theoretically also trigger something else. Could be also some shock, for example. I mean,
Yeah.
Just to check then in the theoretical framework what's the stability you need to dissipate that energy.
Yeah. Okay. Yeah, it's a good idea. Just the one thing I'd maybe be a little bit worried about though is just like the infall, because it's like on a free fall orbit, it kind of really messes up the nice structure of the disk, and so it tends to make the disk much bigger after the infall event. So maybe that would lead to outer regions being colder than they were originally, because the gas is further away, but the size also increases a lot more than the mass does, so that might counteract it a bit. But it's definitely something to consider. Yeah.
One short question.
So you have shown some geometry for the streamers.
Yeah.
What happens if you change these parameters? You assume that's an ellipse. You change what's the major axis.
Yeah, a lot of crazy stuff happens. It's actually kind of hard to quantify because the parameter space is so large. I mean, I think there's a lot that we can do on this, honestly. I think it'd be nice to do like a larger, kind of more elongated streamer like object that internally has some kind of turbulent structure, and so it doesn't all just fall on the disk in a laminar fashion, but you get fragments. That'd be also kind of cool to do, which I think is what's happening in AB Aurigae. You got smaller filaments hitting the disk, but this larger kind of elongated structure around it that's not directly interacting with the disk. Most of it isn't, at least.
Okay, I think we need to move on. So thanks, Josh, again. Thank you. See you with this.